Hello and welcome back. Today's topic in this series of statistics is the binomial probability model. Let's begin. This presentation 5.3, binomial random variable, and note the development team below. Now we want to talk about a particular model called the probability model, which has several features in common, and we'll try and illustrate these to you now. If we toss a fair coin 100 trials, and we're interested in the number of heads occurring in the 100 trials, this becomes a binomial random variable. Binomial means two outcomes. So in the case of genetics, a particular gene type X occurs in 20% of the population. In a random sample of 40 items from the population, how many times do we have an X gene occur in the 40 trials? In manufacturing, 12% of the items on the assembly line are defective. Sample of 25, and how many of these 25 would be defective on average. And also the flu season, 18% of the people have the flu. So we take a random sample, 36 people, truly random sample. We're interested in the number of people who have that flu in the 36. So it consists of a number of trials. On any trials there's only two outcomes, success and failure. On any trial the probability of success is fixed. This is called a probability model, in particular binomial model. And we're going to look at the properties in much more detail. And coming up on the screen here, and we ask you to consider the example of tossing a fair coin. Generally, this experiment, the binomial model, consists of a number of trials. And part two, there's only two outcomes on any trial. And we label these as success and failure, much like heads and tails. And probability of success on any trial is fixed and denoted by the letter P. In this case, the probability of heads is a half. On any trial, the outcomes are independent of the outcome in any other trial. And finally, the interest is in X equal the number of successes in trials. And we're going to see the case here for a general random variable X. To find the mean and standard deviation, we must use these formulae here. And for the special case of a binomial random variable, there are two shortcut formulas given here. The mean is mu equals n times p, probability of success times the number of trials, and so on. I'm going to illustrate that with tossing a coin 100 trials. The number of heads occurs on average, there will be 50 heads, and standard deviation is 5. That's supposed to be illustrated here. Mean is 50. Standard deviation of 5 means that we'll get between 45 and 55, 68% of the time. Now we're going to look at a particular example of genetics. A certain X gene appears 1 in 3, 1/3, and you're asked to verify the postulates of the binomial model here. Pause the screen and write these down. We'll review them. And we're looking at 6 successes and 6 trials. That's 6 X's. In other words, all 6 have that X trait. Each a probability of a third. So the probability of that occurring, 6 successes and 6 trials, 1/3 to the 6. Now, for 1 success and 6 trials, there's 1 X and the rest are all O's. And the probabilities are given here. Or we can have the X in the second spot, and with the probabilities given here. Or it can be the third spot, or the fourth or fifth or sixth. In other words, there's 6 slots to choose 1 at a time, 1 X at a time. Combination 6 choose 1. So there's 6 ways of doing that. Probability of success is 1/3, 2/3 to the 5th. And this is called the binomial probability. For two successes and 6 trials, note we got 2 X's. See them coming on the screen here. And the probability of each one is 1/3 squared, 2/3 to the 4th. That's coming up here. 6 slots choose 2 at a time. Combination 6 choose 2 times a third squared, 2/3 to the 4th. And generally for K successes, in 6 trials. We just modified this to be 6 choose k, 1/3 to the k, 2/3 to 6 minus k. And generally for n successes, for k successes in n trials, we modify the formula as follows: n choose k ways of getting k successes in n trials, each having probability given here on the screen, and that's called the key formula here. You should know this. Now we're going to look at an application of this. We have the claim that 20% of the large herd of animals in northern Canada are infected, and we take a sample of 100, and assuming this claim is correct, 20% infected, we can check that the postulates of the binomial random variable are met here. Theoretically, this is an infinite population, enabling us to make these claims. The mean or expected value, 20% times 100 is 20. We can expect 20 of the 100 to be infected. Standard deviation is 4. And we're saying that that distribution of x follows that shown on the screen here. Mean of 20. Standard deviation of 4. And this is variability about the mean, plus or minus 4. 60% of the time we'll get a value between 16 and 24. Now let's evaluate the claim. 20 successes in 100 trials. Compute the z-score. X is 29 minus 20 over 4. 2.25 is greater than 2 standard deviations. This is a somewhat rare or unusual event if the claim is true, and this tends to suggest that, based on this evidence here, we would suggest that the observed results tend to refute the claim. Now looking at the generated probabilities here, to get x greater than or equal to 29, it's the sum of these numbers here. You see them coming on the screen here. About 2%. Somewhat rare, 2 in 100. If the claim were true, this calls into question the validity of the claim. And that's the end of presentation 5.3. We ask you to take notes as required and continue to presentation 5.4.